Okay, yeah, thank you very much for inviting me to Limini, even though it's only virtual this year, but things will get better again, I hope. So, yeah, I'm going to talk about joint work with Rudolf Frei from UCL. And yeah, so originally I was planning to do a Blackboard talk on my drawing tablet, but I found out that I'm not fast enough at writing legibly to give a talk in this way. So I've prepared my slides. They're still handwritten, but I've prepared them in advance. I hope they're somewhat legible. Okay, so if you're given an extension of number fields, capital K over little k of degree n, then of course there is the field theoretic norm map from capital K to little k. And then if you fix a basis omega 1 up to omega n of your extension, then you can write the norm map in this basis. And this is a polynomial with coefficients x1 up to xn, and it's homogeneous of degree n. And such a polynomial is called the norm form, or that's what I call the norm form today. And given such a norm form from a number field, or from an extension of number fields, and a number, alpha, an element of the small number field, then one can look at norm form equations, where you say n of x1 up to xn is alpha. So norm of x1 omega 1 plus and so on up to xn omega n should be alpha. No, these are very classical objects. Two kinds of questions at least have been studied extensively. First is, well, given an alpha and a number field k, giving you the norm form, then you study its solutions. Yeah? Are there solutions, and so on. Secondly, given just a number field k, then people have also studied the set of alpha for which this equation has a solution. For example, asymptotics, how large this set is, and so on. Okay. And in this talk, in this project, we were looking at this sort of from the other way around. We start with elements of a small number field with k, and what we study are extensions such that all of these alphas are norms from the large field. So it's in some sense the opposite problem to these questions above here. We don't fix the elements that we fix the elements that should be norms, and we vary the extension field. And then, for example, one can put some restrictions on capital K. One can fix the degree. Okay. One can only look at extensions of a given degree, and for example, with a given Galois group. And one could also say that the local extension at certain, probably finite in many places, should also be prescribed. So that's the kind of problems that I'm looking at. Let me show you a very simple example of this. So I want to find an Sn extension of Q with prescribed norm alpha. So a number field of degree n, whose Galois group of a normal closure is the full Sn. And alpha should be norm from this field. I can do this by just writing down a generic polynomial, x to the n plus an minus 1, x to the n minus 1, and so on, for which the constant coefficient is the correctly scaled alpha. And then I just choose my polynomials an minus 1 up to a1, sufficiently generic so that Hilbert's irreducibility theorem guarantees that this polynomial has Galois group Sn over Q. And then I just take k as my number field generated by a root of this polynomial. Then it's an Sn extension. And just by the way in which this polynomial was constructed, alpha is a norm, namely the norm of this element beta, because it's here in constant coefficient with the right sign. Okay, so that was easy. And that's the situation for Sn extensions. what I really want to talk about is the polar opposite of Sn extensions. It's abelian extensions. The Galois groups are as small as possible, as simple as possible, given a fixed degree. So from now on, I fix my number field little k, and I fix a finite abelian group G. This should be the Galois group of my extension. And I also fix a set A of elements alpha 1 up to alpha t of little k that should be norms from the extension. So the first result that I want to present here is this one. That's due to myself, then Lofram and Rachel Newton. It's pretty recent. And it counts extensions k that are abelian with Galois group G, such that all these alphas, all these elements of A are norms from capital K. And it counts them with respect to a quantity called the conductor. So this is this phi of K over K. So that's the absolute norm of the conductor of my extension, and this should be bounded by B. Yeah. So that's a counting function of G extensions of little k, in which all alphas are norms, and whose conductor is bounded by B. And it's well known that given any bound B, then there are only finitely many G extensions with conductor bounded by B, and we are counting a part of them. And this counting function behaves like a constant times B times the power of the logarithm of B. All of this can be made very, very explicit. So C is a positive constant. One could also write this constant down explicitly, but it's ugly. And this exponent here, this phi, has a very nice form. It's the sum over all elements of the group, 1 divided by the degree of a field extension, kg over k, where g is the order of this group element g, and kg or kd for any d is this number field that you get by adjoining to little k a d root of unity and d roots of all these elements alpha that you want to make norms. Okay. So this constant here is positive. So in particular, our theorem has the corollary that such extensions always exist. So that's the corollary here. Given any number field k, any finite abelian group G, and any finite set of elements of k, then there is an extension, capital K, with Galois group G, such that all these elements are norms. As far as we know, that was new. But it's a corollary of a density result. And in particular, it's not quite clear how do you actually construct such an extension. We know that they exist, we know that there are finite, infinitely many, and we can count them, but it's not clear how to construct them. And that's what I worked out with Rudolf Frei. So we found a constructive proof of this corollary. And since it's about abelian extensions, this uses classical theory. So, and then in my talk, I was planning to explain this construction to you. And in the end, to show you an example. So here is a summary of the facts from classical theory that I'm going to use. It says that extensions, capital K of little k, together with an isomorphism from the Galois group to our prescribed group G. So these pairs of an extension plus an isomorphism are parameterized one-to-one by some other objects. And these are continuous and surjective homomorphisms from the ideal class group of my number field little k to my group G. Yeah. So it should be surjective and continuous. The topology is not going to play a role in this talk, so you can forget about this continuous if you want. So the ideal group here, this IK, written down a definition here, it's a restricted product over all places of my number field. And then I take the local field at this place. So that's a restricted product. This means that an element of this is a unit, a local unit in OB star at almost all places. Yeah. So that's the ideal group. And then K star, so the unit group of K embeds naturally in this just by mapping it to a copy of K star in each vector, and then you can mod it out. It's the ideal class group. Okay. So here I've written down this parameterization again. So pairs of extensions capital K of little k together with an isomorphism of the Galois group to G, parameterized by these subjective continuous homomorphisms phi. And then there is also a norm map from the ideals of capital K to the ideals of small k. I'm sorry, forget about this star here. Maybe I can. No. Yeah. So this shouldn't be there. This also. Okay. So how does this go? You take an ideal of the big field with local components alpha w for w place, and you map it to the ideal with local components at place v. So v is a place of small k. And the local component at v is the product over all of the places w of capital K extending your place v. And then you take the local norm of the coordinate there. So that's the norm map on ideals, and it extends the field theoretic norm. And then another important fact from classical theory is this one. So if phi corresponds to my extension k, then the kernel of phi is the norms of the ideals of k. So that's how you can detect norms using classical theory. And of course, it's all modulo little k. So this is good news and bad news. The good news for our problem is that classical theory is very good at detecting norms, or to be more precise, everywhere local norms. So that's just elements in here that are norms of ideals. On the other hand, since everything happens modulo the actual global field that you're interested in, the bad news is that classical theory is not good at detecting global norms, because everything that's global is sort of getting modded out. So what do you mean by global norms? Global norms are just norms from capital K. So that's the elements that I'm interested in. And here I have my everywhere local norms. So those are elements of little k that are maybe not norms of elements of capital K, but at least they are norms of ideals in this way. Yeah. And clearly, everything that's the norm from an element is the norm of an ideal. So we have this inclusion here. So how we can go about still detecting global norms is by something called the Hassan norm principle. So we say that our extension capital K of little k satisfies the Hassan norm principle if the following holds. So if we have equality here, if the global norms are not only contained in the everywhere local norms, but if they're equal to them. And that's good, because if the extension turns out to satisfy the Hassan norm principle, then we can again apply our classical theory to detect global norms, just going via everywhere local norms. So here are two classical results due to Hasse about the Hassan norm principle. The first is that it holds for cyclic extensions. So whenever capital K over little k is a normal extension whose Galois group is cyclic, then it satisfies the Hassan norm principle. So we always have equality here. And again, the bad news is that for the simplest non-cyclic extensions, which are biquadratic ones, so Galois group Z2 times Z2, there are already counterexamples. So this one is due to Hasse. If you join the square root of minus 3 and of 13 to Q, then this extension does not satisfy the Hasse norm principle. And just because it fits in, here is another result from my paper with Dan Lochran and Rachel Newton. It says that if you fix an abelian Galois group, then 100% of all G extensions of little k satisfy the Hasse norm principle. So by 100%, I mean natural density 1 if you order them by this absolute norm of the conductor. You don't necessarily have to count number fields by a conductor. I mean, the conductor is really nice invariant to count abelian extensions by, but another, maybe from some perspective, more natural invariant to count number fields by would be the discriminant. And it turns out that when you count by discriminant, then things are more complicated. Yeah. Then this is actually not true for many groups G. Okay. That's just an aside. Good, so we have the Hasse norm principle. Tate has formulated a powerful criterion for when the Hasse norm principle holds for an extension k over k that is normal. Yeah. So I write G for the Galois group of k over k and GV for the decomposition group at the place V. So that's just the Galois group of a corresponding local extension for any place W lying above V. You know, all of these are canonically isomorphic. So it doesn't matter which W you choose. And then on the right-hand side here, this object is called the knot group of the extension capital K or little k. And it is everywhere local norms, so those elements of little k that are norms of, sorry, this should be an ik. Maybe I can fix this. So elements of little k that are norms of ideals, and you mod out the global norms. And this object is so Tate has shown that this is isomorphic to the kernel of a map between cohomology groups. So you have the third cohomology of G, so third Galois cohomology of k over k, and you go to the product over all places of little k to the third cohomology of these decomposition groups by the restriction map. And the kernel of this is isomorphic to the knot group. So to satisfy the Hasse norm principle means that this group is 0. So in other words, your extension or extension k over little k satisfies the Hasse norm principle if and only if this map here is injective. And this already, so we already used this in the paper with Dan Lochran and Rachel Newton in the following dual form. So you just take the dual of this map. So then this goes from the sum over the exterior square of the decomposition group to the exterior square of G, and it should be surjective. So this form was actually heavily used in this paper with Dan and Rachel, because I mean this is quite explicit, and yeah, I mean it's easy to apply. So we have this criterion for the Hasse norm principle, and now we're going to apply it. To do so, we need to see how class field theory detects these decomposition groups here. Yeah. So I'm explaining this here. So if my extension is given by this surjective homomorphism phi from the ideal class group to G, and V is any place, then I can look at phi V, and phi V just composes phi with the embedding of my local field into the ideal class group. Yeah. And then this decomposition group GV, as a subgroup of G, will just be the image of this map phi V. So everything fits together very nicely. So given all this, I can now formulate the goal of this construction. So which kinds of homomorphisms are we trying to find? We want to construct homomorphisms phi such that at all places, these elements alpha 1 up to alpha t, which I want to be norms, should be in the kernel of this local map phi V. Okay. So what does this tell me? This tells me that all the alphas are everywhere local norms. If you remember from earlier, I've shown you that the kernel of the global map phi corresponds to norms, and the same holds for local classical theory as well. So this first condition here says that all the elements alpha are everywhere local norms. And the second condition is the one that we get from Tate's criterion for the Hassan principle. It says that the natural map going from the direct sum of these exterior squares of the images of phi V, because the images of phi V are just the decomposition groups, as we worked out here, to the exterior square of G, they should be surjective. And then this condition ensures that the Hassan principle holds. So taking these two together, we see that all these alphas then will not only be local norms, but they will in fact be global norms as desired. So now we construct such homomorphisms phi that have these two properties. So it's not a problem to do all of this over arbitrary base number fields little k, but it's just notationally a bit easier to do it over Q. So for now on, I'm going to restrict to little k equals Q for this presentation. And similarly, I'm going to restrict my group G to be of this form, Z mod Ez to some power R. So you can go from these special G's to general abelian groups just by taking E to be the exponent, and well, then you can reduce to the case of these groups G. And you just have to use some more notation to get rid of this restriction that little k is Q. It gets a bit more complicated because, as usual, infinite unit group makes problems, and well, non-trivial class group also creates some problems, but it's sort of well known how to deal with this. Okay, so now if little k is Q, then one can describe this ideal class group quite simply in a more concrete way. Yeah, it's the group of positive real numbers times the units of Z hat, so the profinite closure of Z. So I've written here what this is or how I see it. So units of Z hat is the product over all primes, and then I take the local units, so p-adic units, ZP. Okay. Now, I'm going to construct these homomorphisms from units of Z hat to G. And then, of course, one can extend it trivially to this vector to get a map from the ideal class group to G. Okay. So we've reduced to finding such a homomorphism from Z hat star to G, still satisfying our two properties. How am I going to do this? I need some primes, P1 up to PR. So this R here is this R. So the E rank of G. Okay. So I want R primes that are all congruent 1 mod E. So E was the exponent of G, such that my elements alpha that I want to be norms are local units at these primes. And moreover, if you reduce them mod Pi, then there should be Eve powers in the residue field. Okay. So all of these conditions are of Chebotarev type. So Chebotarev density theorem guarantees that there are infinitely many such primes. And if you take effective versions of Chebotarev's theorem, then you can also see how long you need to search if you're really unlucky. But you will find such primes. Okay. So, given these primes, I have everything that I need to write down the first version of this homomorphism phi. So it goes from Z hat star. Remember, this was the product over ZP star for all primes P. And I just ignore all the factors at all primes P except for my primes Pi. Yeah, I just ignore all the other factors. So it goes to this finite product over ZPi star. And then in each component, I can reduce mod Pi. They go to the finite product for I from 1 to R to the residue fields, FPi star. And then I reduce some more. So here I've forgotten something. Yeah. I go to, in each factor again, to FPi star mod Eve powers. So, since Pi was congruent to 1 mod E, FPi star is a cyclic group of order divisible by E. So if I take it modulo Eve powers, then it's a cyclic group of order E. And therefore, this product here is isomorphic to Z mod E Z to the R, which was our group G. Okay, so I have constructed this homomorphism phi from Z hat star to G. It's obviously surjective because each of the components is surjective. And also, all the alpha i's are in the kernel of this map because I've chosen my primes in such a way that they are Eve powers in these FPi star. So here, from here on, they are 0. Yeah. Okay, so what does this give me? I have this surjective map. This gives me an extension with Galois group G of Q. So G extension K of Q. And all the alphas are norms of idels. So everywhere local norms. So what's missing is how I make them global norms via the Hassan Principle. So now I need to take a look at how to implement this second part here, its criterion for the Hassan Principle. Okay, so how can I ensure that the Hassan Principle holds? I need to use some more primes. First of all, so this Z mod E Z to the R, this was our group G. Okay, so lambda 2, the exterior square of G appears, and the exterior square of such an Rth power. I mean, I've written it down here, but it is. So you take E1 up to ER, the standard basis of Z mod E Z to the R, and then you wedge any two of them together and take the Z mod E Z module generated by that, and then this gives you the exterior square of Z mod E Z to the R. So these here are the bases. Okay. So now instead of taking just R primes, I now need to take R over 2 pairs of primes, PL, QL, that satisfy the same properties as above for now. So they should be congruent 1 mod E. And all of my alphas, so all of the elements that I want to be norms, should be Eve powers mod PL and Eve powers mod QL. Yeah. I have M such pairs, PL, QL. And then I start by constructing a homomorphism, which I call phi prime, in exactly the same way as before. So I go from z hat to the z hat star. Sorry, I go from z hat star to the components at PL and QL. Then I go to the residue field, and then I reduce modulo Eve powers. So I end up here at the product over L from 1 up to M. FPL star mod FPL star Eve powers times FQL star mod FQL star Eve powers. And then again, each of these vectors is Z mod EZ. So here I have Z mod EZ squared. So I have M copies of Z mod EZ squared. And I call this G prime for now. And now, so about this here, I'm going to say a little bit later on, so that's sort of the most technical part of our construction. We now find a basis, F1, F1 prime up to Fm, Fm prime, so 2n basis elements of this G prime that have the property that each FL, FL prime is the basis of the image of the local field, KPL star, yeah, for all L. And then so let's just assume that we are able to find such a basis for now. Then I construct a second map, a psi, and this goes now from G prime to a group G. Yeah. And the way in which I do this is I take all pairs of elements of my standard basis of Z mod EZ to the R, enumerate them in some way. Yeah. So I have these M pairs, and then the pair FL prime from this basis up here of, so this pair FL prime, which forms the basis of phi prime of KPL star. This should go to the elf pair EI, EJ in this enumeration. Okay, so it's defined on the basis of G prime, so that's completely fine. It's good, it's objective. What am I going to do with that? I define my phi, so that's the homomorphism that I want to construct, that I'm interested in, as the composition of these two. So we go from Z hat star first to G prime and then to G. And then since both of these components are surjective, the whole thing is surjective, and we still have this property that phi of all the alpha j's is 0 for all my j's, because if you look back at phi prime, then phi prime goes here to PL not FPL to the Eve powers and QL, FQL, not FQL to the Eve powers, and my primes PL and QL were chosen in such a way that all alphas are Eve powers. So again, from here on, the alphas are 0, mapped to 0. Okay, so we have still preserved this condition that we had previously, but now we have way more factors, and we can use these factors to make the Hassan principle work. So if you look at the exterior square of phi of some local factor KPL at the prime PL, well, so phi of KPL is psi of phi prime of KPL, And a basis of phi prime of KPL are these FL and FL prime. So the exterior square of phi of KPL is a cyclic of order E, and here is a basis element. But now we constructed this psi map in exactly such a way that this pair FL prime goes to EI, EJ, or for a pair EI, EJ of basis elements of G. Yeah? So that's how we constructed the map here. So if I take now the sum over all my pairs of primes, PL, QL from 1 up to m, of the exterior squares of the image of KPL star, then this covers my exterior square of G, because that's just the direct sum of all cyclic factors of this form. Okay, so we have guaranteed that the Hassan principle holds. I had this assumption earlier that we are able to find a basis f1, f1 prime up to fm, fm prime of G prime, such that each FL, FL prime is a basis of this phi prime of KPL star. So now I should justify how we can achieve this. And to do so, we first need to see how we can identify this local field, KPL star, inside of our domain set hat star. So PL star, I mean, that's a local field, so it's a copy of the local units, set PL star, times powers of a uniformizer, and of course PL is a uniformizer. So it's clear how set PL star maps into set hat, because set hat star was just a product over all these set P star, and PL is one of these factors. So I just map set PL star to the PL factor here. And for this uniformizer, PL itself, so this does not appear in any of these factors. But I can move it around a little bit, because so this set hat star, this is supposed to stand for the ideal class group of Q. And in the ideal class group, everything is modulo Q star. So I can multiply this, for example, by, well, PL inverse, and then this here. So PL inverse, and 1 as the PL factor, PL inverse, and so on. So this is the same element as 1 and so on, up to PL 1 and so on, 1 in the ideal class group of Q. Okay, but this representation actually gives me this element as an element of set hat star. Okay, so that's what I'm mapping this to. And then, essentially, what I have to do to ensure that I can find such a basis is to choose my prime QL in this pair, PL, QL, in such a way that x to the e minus PL is irreducible over FQL. And of course, that's again a Chebotarev condition. So once I have this, this map here is surjective. So what's this map? We go now from KPL star and we embed it into Z hat star in the way that I've explained here. Yeah. And then I just go directly to the factors at P and Q, to the local fields, and to the local fields modulo if powers. Yeah. So now this here is hit by this ZPL star factor. And here, this condition that x to the e minus pl is irreducible over fql, this guarantees that this is generated by the image of el itself. And therefore we are surjective up to here. And by the way, which I've chosen my primes, this is again isomorphic to Z mod E Z squared. Okay, so what I've shown here is that T prime of KPL star is isomorphic to Z mod E Z squared. So it has a basis consisting of two elements, FL and FL prime. And then what I need to make sure is that these basis elements fit well together, so they actually build a basis of G prime. And we do this in the paper using an inductive process, which is not terribly complicated, but maybe a bit too much to explain it here on slides. So I won't say anything more about this, but that's in principle how it works. So let me remark that everything that I've told you so far, meaning it may look slightly abstract, but everything is very concrete and can be implemented on a computer. And we have done so in a sort of, we have not really implemented it in Sage in the form of a package, but we have Sage worksheets in which we just can enter our data and then combined with some computations by hand, we can get results. So let me show you an example here. Just worked this out today during the lunch break. So I want to find a field K that's abelian over Q with Galois group Z mod 2Z cubed, so a triquadratic field. And I want 2 to be a norm from this field. So my rank here is 3, which means that I need 3 over 2, so 3 pairs of primes PL, QL. And these pairs of primes, they should satisfy these various conditions that we've discussed. So here are the primes, so 17, 41, 73, 113, and 89, and 97. So that's P1, Q1, P2, Q2, P3, Q3. And well, so that's the homomorphism specifying my extension K. Now this is very explicit and concrete. I mean, you can read off the conductor of this if you think about it a little bit. And together with some data that comes from the construction of this, one can also read off the splitting primes. So this is a list of the first few primes that split in this extension. And then, of course, if you do constructive class field theory, then knowing the conductor and knowing and being able to generate all the splitting primes is enough to give you equations for your field. I mean, that's implemented in Magma, for example. And in this particular case, Magma took maybe a second or two or so to compute this concrete representation of the field. Okay, I think that's all I wanted to say here. So yeah, thank you.